Maybe we need to switch also like or close the meaning of the people saying. But we can switch
all the lights. Okay.
Yeah. Oh, now it's changed.
Yeah.
Now it's time to continue our session with Vitto and speech about Guzi, European stuff, and others.
Okay. Thanks a lot for the host and for the nice introduction. So yesterday we went a little bit fast due to the national holiday hustle, and I apologize a little bit for that. And as we already went through all the history of the discovery of graphene, the invention of graphene heterostructures, and the beautiful physics of flat chain bands of moire superlattices made of, for example, graphene and their other materials. And yesterday we also went through some kind of new tools, which is a quantum superlattice. And this thing can bring up some new physics. For example, can boost the quantum Hall effect that allows one to see this beautiful phenomenon in higher temperature and lower magnetic field regime, which is toward one more step in application-wise. And today, let's continue. Before we go to the next slides, I would like to say a bit words of today's lecture. The main works is about our other experiments using the same technique as yesterday I introduced you. It's about same material which creates within a crystal and induce some new physics. And all the experiments are done by my students, and two of them are actually here in the classroom. It's Kai Yin and Iman. So I will speak in more details. First of all, let's begin with a more interactive way. Is there anyone who is doing, let's say, transport measurement or have some experience on either theoretical or experiment? Great. Oh, a lot of you. Great, great. So, Misha, please, can you tell me what is your classification or definition of different conductors? Do you have any ideas how many kinds of conductors we have to our knowledge?
Conductors or just types of instruments?
Anything which is conducting, can you classify that into several categories, let's say?
There's a gap or no gap?
Fantastic. Gap ones and non-gaps. And this is defined from, let's say, the electronic structure, right? Is there any other ways to classify that? By any kind of measures, observations, say, other suggestions from the audience?
Maybe.
Yes, please.
Maybe connectivity. So.
Awesome. Yes.
I mean, you can look at the T equals 0 limit of the connectivity. It's finite.
Look at
finite infinite or 0.
The ground states of the connectivity.
Yeah.
Is that what you're saying? So you have a metal, something like that?
Yeah. Metals.
Yes, metals and
superconductors and
semiconductors and insulators. Anything else?
Like
Disorder?
yeah, like what type of disorder?
Like insulators, including the disordered system, right? Is Anton here today? Anton, no? Okay, the man of disorder is not here today. Sorry for that. So disordered system is one of these insulators. That's correct. And insulators is including not only disordered system, right? Include also more.
That's not what I meant like which type of disorder gives the good.
You mean, okay, I'm sorry. Yeah, you are, let's keep that. Let's keep that. You're saying that by the number of disorder or the level.
By type. Like whether or not it's phonon interactions that are not as impurities, electron-electron interactions.
Phonon interactive. Can you give some example?
Well, any usual metal.
Any kind of metal?
Yeah.
So it's actually, let's put another way for experimentalists. The phonon interactive disorder system, how does the RT curve look like? Can you draw that? The resistance and functional temperature should look like. So, if this some kind of limitation and residue goes like that, is it still this behavior or is going up?
Well, no, the limit when it goes to zero, but the limit is impurity.
The zero is here. There's some residue.
Yeah, but the residue is
finite.
from impurities. From like
Okay, so you call this a metal, right? Basically, it's a metal. This one, right? And this is an insulator or semiconductor. And for superconductors, you may have two kinds of either transit from metal to zero resistance, or transit from insulator to zero resistance. So there is also a superconductor. Yeah, that's right. So let's say in the coming sections, we're focusing more on insulators. And according to the great audience, thanks a lot for you have been great. So according to the suggestions from you, there's a disorder-induced insulator. There can be also gap ones. It's also insulator. Any other kinds of insulators that we may have heard or encountered ever? No.
Multi-insulators interaction used.
Fantastic. That's the answer I want to hear. Multi-insulator or other kind of interaction-induced insulator is a great family that has been paid much attention nowadays. Even let's say in the past decade. Multi-insulator is a very one of the good examples. There's also excitonic insulators. Excitonic insulator is also a interaction-induced insulator, which is due to the, say, Bose-Einstein condensation. Because when we have, let's say, a semi-metal with a narrow gap, small ones, or semi-metal with this kind of crossing of conduction band and valence band, electron hole puddles, there's some overlap. In these kind of narrow gap semiconductors, electron holes can always find themselves in a position where they have a lifetime. They could be paired into electron hole pairs. We call that excitons. And this is something which can combine two fermions into a boson, right? So any bosons, if you have the temperature lower enough, and there was some mathematics behind, which is very similar to BCS near field theory, and you will have a condensate. A condensate where all these exciton pairs, they will just collapse into one point, and the global phase is insulated. So this behavior is fascinating. It has been established theoretically since a very long time, but experimentally it's so difficult to spot that, to, let's say, distinguish the exciton insulator from other things. And I'm going to show you something experimentally, and we believe it might be a family of this kind of interaction-induced insulator, but which, let's say, still there are some open questions, and I hope I can hear your advices or, let's say, interactions more in the coming slides. Okay? So let's continue with the system that I introduced you yesterday. It's mainly about still within, these are the peoples involved. I would like to make an acknowledgement first, because we are now really focusing on some experimental results recently done in our labs. So we have collaborators from different universities, and there are some providers of HBN crystals from Japan, NIMS, and our theoretical collaborators, Professor Sidai and Shanghai, and Jianping Liu from Shanghai Tech. And here is Kenny, who is sitting in the audience. So he has a very shy personality. I hope you can discuss more with him if you want to know any more experimental details. That's the picture I would like to say at the very beginning. So this is just some introduction of background, and we're not saying definitively the observations in the coming slides are external insulator condensate or any kind of, but we may attribute that to the originality of EI-induced insulating behavior. So when you have excitation of electron holes, they will pair into pairs, and there are some characterization length to describe this system, which is called ball radius, which is in this picture. They have some kind of radius which is defined as AB, and then this system, once they condense into an insulating phase, imagine if we measure the system using transport again, we will have a IV curve look like this one. This is just a schematic drawing. It's not a real measurement. So there is a gap, of course. When you apply some voltage, you obtain zero current. That's somehow you say it's an insulator, right? Basic definition. At some point, imagine the electrical field is large enough, all the pairs would be broken, and then they will become free again, so the system will be conducting. Something like superconductor, but it's reverting. So in superconductivity, it's the axis will be I and V. Here is the V and I, and there are some slight difference, and that's the basic introduction of this. So we would expect di over dV, the differential conductivity in the system with external compensation, will look like this. Okay, this is really very similar to superconductor, but kind of inverted. All right. So there are many theories in ancient years. Some famous paper from the JTTP paper in 1965. So they classify this extonic insulator in two regimes. Basically, that's the same matter, but with different limits. Okay, one is the BCS limit, when the density of them is very large, so you have a lot of excitons. And there is another limit, which is BEC limit, at the regime where the density of them is very diluted, like this Bose-Einstein condensation limit. And there is some kind of crossover regime where the two numbers are around 1. Okay, so this is some kind of phase diagram, and it's not a quantitative one; it's just qualitative figure. So of course there are other predictions saying that this is interesting because theory says extonic insulator may happen even at room temperature. So that means the interaction, as long as it's strong enough, you should have some new class of insulators which you can break them by electrical field and then tune them by the density, and it can happen at room temperature, which is great for, let's say, fundamental research and application-wise. And there's a large library of materials. As long as we have a narrow-banded system, they should have electron hole pairing, and there should be possibilities when you cool down the system to a low temperature enough at a TC, you will see some kind of behavior, critical ones, due to the phase transition. For example, if you measure conductivity as a function of the temperature, here is the resistivity as a function of temperature. There are slight some difference, but general behavior is the same. It's just that the system behaves into a regime where no conductivity could happen, and the conductivity will drop to 0. And this is very challenging for experimental measurement. Can anyone tell me, those who do transport measurement, anyone tell me why this is challenging to measure very large resistance or very small conductivity?
You have leakage current everywhere. It's hard to measure.
Yeah, it's that's the one.
You apply noise.
Exactly. Yeah. Yes. So basically, when the system is super insulating, you apply some voltage, you collect 0 current, and if the circuit is open, you can also get some fluctuation. That's noise. Noise would be comparable when your resistance is large enough. So no lock-in technique can be possible. No STM can be possible anymore because the system has no density state. So you cannot do the experiment by a conventional low-frequency lock-in amplifying technique. And also, the phase is also very weird because in superconductors, the Bose-Einstein condensation, you will have Josephson effect. For example, you have a junction that connects two phases of Bose condensate phase left and phase right, you will have a magnetic field tuned flux changing in the whole system. The interference will happen. But when the system is insulator, it's excitonic insulator or excitonic condensation phase, you will have nothing similar to Josephson effect. Unless someone could build some new equations. I don't know if it's possible. Probably possible, but not yet now. You know, if someone can tune the phase of a excitonic insulator or excitonic condensate by some means, you know, because there's no responsibility, no response to magnetic field, there's no response to many things. It's insulated basically. So we cannot have an analog to Josephson effect. It's very difficult to probe the phase definitively. Okay, there might be some combination that you can measure by optical measurement to determine the real excitonic gap optically, and at the same time you do the transport measurement and combine the two evidences together. That's possible, but still, all the measurements is difficult, and so far there's literally no direct evidence of excitonic condensate in a bulk metallic system. But there are some other ways to do this experiment. For example, I'm going to show you some backgrounds. In 2017, there's a very good paper using a technique called momentum resolved electron energy loss, which is EO's spectroscopy, and they found that except for there's a electron excitation at this K vector, when you cool down the system from 300K to 100K, there are two new energy showing up at different K vectors. So according to their technology, which, you know, I'm not an expert in that, but according to the paper, what they claim is that what they're probing is a zero energy limit. So at zero energy limit, there are different Ks. So this is only possible of a excitonic condensate. That's the major claim, and the material was 1T phase titanium diselenide. So this is a narrow gap semiconductor, and that's an optical spectroscopy measurement evidence. There's no transport evidence. And also there are some other, say, routes to allow us to explore the phenomenon of exciton condensate. You know, it's not directly probing the transport, but you can indeed construct some materials using two-dimensional semiconductors. For example, this one is from Cornell group, Kim and Mac, in 2021. What they constructed was a space 2 layers by a very thin HBM layer, a tungsten, I cannot see that, tungsten diselenide and molybdenum diselenide. These two materials, if you tune the two gates to adjust their, let's say, population of electron holes, at some point they will form a regime where the compressibility of the system changes dramatically. The compressibility can be defined as, let's say, the pi -1 equals to the chemical potential change per particle. So when there is a gap, so taking out a particle or adding in a new particle costs huge energy. That compressibility goes to 0. So that's the definition, and what they can probe is using a capacitance measurement which is proportional to the compressibility of the whole two-dimensional electron gases in the system. And they obtain a new gap, which can only be explained by the existence of electron hole pairing condensate, which happens in the system. And here we have to say this is an indirect one, because the whole system, you cannot, say, break down the two layers. They have to be working together. The interaction between electron holes has to be interlayer ones. And that's some kind of measurements can tell us there is indeed a possibility to build up the system that shows excitonic condensate. There are a lot of other evidences. I'm not going to go through every detail of the experiments, but one of them is very interesting, and I have to introduce you a little bit in case you didn't know that before, but I'm sure that many of you should have known this. So in a regime where we are in a quantum Hall regime, the bulk are all localized. There is a bulk insulator, and the H channels are transported in a balanced way without backscattering closely. So in this regime, if the two layers are both in the quantum Hall regime, And if you tune them correctly by the two top and bottom gate, they will find some plateaus where it happens at a fraction of the original plateau. Like this one, it's a temperature dependence new plateau that says the top layer and the bottom layer, they shares electron holes in each layer. And at that time, there is a counterflow. The whole system shows a superfluid behavior. So this is a new experiment done in old scheme because it has been already proven in gallium arsenide quantum wells like 25 years ago. It's just that in graphene you can go to even thinner limit when the two layers of graphene are closer or in a more distant way by just adjusting the thickness of space in HBM. So this two-dimensional material has some power of tuning some detailed tuning parameters in the system, which wasn't possible in gallium arsenide quantum wells. And there's also some other experiments more recently from Corradin's group in Columbia University. They show that in the equilibrium conditions, there's also a tectonic gaps showing up in between number levels due to the polyblocking principles. So there are a lot of schemes that can show directly or indirectly or in the quantum origin excitonic phases that shows possibly condensate and some superfluid phases. So what we are more interested in is in the transport evidence. There are indeed, in 2021, Zheng Wu's group from Nature paper, they reported that in tungsten ditelluride, this kind of system, when HBN is encapsulating tungsten ditelluride, they use the different electrodes in all directions to probe the anisotropy. And what they found is that the whole system can show a very insulated regime, which the resistance is about 120 megaohm. 120 megaohm is almost, if you measure your body resistance, I think it's approximately that kind of regime. It's very resistive. Supposedly, electrons should be quite localized. They should be not able to do any kind of quantum oscillations in our conventional picture. But what they saw was, counterintuitively, there's oscillations, which is very bizarre in this regime, which is very resistive. So 120 megaohms, still the system is showing quantum oscillations. The claim that this is due to, in this tungsten ditelluride, there are some electron hole pairing inside the plane, and they show this is an evidence of excitonic insulator. So apparently this might be true or might be not. So later on, there is another paper from PRL saying that doing this experiment using a graphite as a bottom gate is a problem because those quantum oscillations might come from the graphite itself, because even though the graphite is thick enough, you still have some quantum oscillations. And they use the same material. Instead of using graphite as gate, they use another very conductive two-dimensional material as gate, and the oscillation disappears. So this is not a very good example of definitely saying that excitonic condensate can be probed by transport in bulk materials. Okay, that's one of the examples. Even though that later on the same group, the one who reported the behavior of STH oscillation in a very resistive regime, they continue to work and using a very complicated the local spectroscopic technique. Like STM, they saw indeed some gaps showing up, and there are also other techniques to prove that there is some gaps. But we know that these kind of gaps cannot be, say, a strong enough evidence to definitely say that these phases are excitonic condensate. So what can we do in other examples? There we go. With all these background, I would like to now remind you again, there is a family of insulators which might come from the interaction of electrons or kind of condensates of BCS type. And these kind of insulators is very difficult to be measured, and they're supposed to exist in many systems, but almost zero evidences have been done directly in transport. And we would like to say, in the coming example, there might be some evidences, and still there are open questions. Okay, let's continue our slides. So we say at the first section of this lecture, I introduced to you that a small gap can be opened in binary graphene due to this kind of let's say, conduction band and valence band crossing, and there's a hybridization opened single particle gap, and that gap is going up to like about 100 millieV. We know that room temperature 300 K is about 25 millielectron volts, the energy scale. So the gap sounds to be large enough, and indeed people can obtain that. And this kind of thing, if you look into another way, for example, we say this original gap of biodirection, if you apply a electrical field, the system will become into a gap state where the gap is a single particle gap. There is no electron interaction or whatsoever, but the gap is about a few tens to 100 eV. So this is a pretty good scenario for us to study some kind of possibility of exciton behavior, and that's obvious. So some experiments from early days already checked the excitons inside of that. There's one of the examples. They saw that indeed there are some electron hole pairing showing up at the vicinity of charge neutrality point, and that's obvious. And there are also theoretical considerations done in a more simplified case. I think this is an AA stacked graph, where they didn't consider the AB structure of the material. What they saw in this theoretical consideration is that due to this interaction between interlayer electron holes, couplings at this direct point, there is a huge gap opened up, and which should maintain at 300 Kelvin. And this is something, let's say, inspiring for experiments, because imagine if you have a way to tune or to enhance the interaction of a bilayer system at the charge neutrality point. You find a way to enhance the interaction somewhere in the layers. You should be able to open a larger gap than this one. And supposedly that one, the new gap, will be more favorable for us to construct nanoelectronic devices out of that.
So,
yes, please.
This gap opening is in one valley or it's from two valleys?
It's from both valleys.
So the left picture is one valley and this one is two valleys.
This is one valley, yes.
And the right one is two valleys.
So this is the EX equal to 0.
But in the right one you have some hybridization. Hybridization is what to do.
This is one valley.
This is
So
all
it's
valley.
also at K. Yes. You have another set of that.
So these two things.
It's just you pull down one of the band down, another up. Two little hybridization opens this kind of gap.
And then, but going, making it up and down, it's by means of what?
By means of vertical electrical field. Yeah. So you change the chemical potential from electron holes. The two particles they behave differently. There is a hybridization opened single particle gap, and that's from one band. Yeah. So there are some details. Some even more details. There could be possibility to tilt this kind of gap behavior, and there's within one valley there could be like another behavior of excitons. The very subtle details inside. There are already some paper from Ensign's group in Switzerland, if I remember correctly. They did some experiment to show that exciton-induced insulators can happen in this kind of band structure by tuning the two gates. Let's say that means the displacement field and the carrier density. In different regions, you will have that. And then here we say that again. So in this paper, it reminds us that the interaction strength of monolayer graphene is somehow proportional to inversely proportional to dielectric constant of the environment and Fermi velocity, and there are interlayer interactions between two layers also defined on beta, which is a function of external electrical field. We already knew that. And there is a distance between two layers, which is given by the material. We cannot play that too much, so we can see that as a constant. There's also a Fermi velocity at play in the denominator. Okay, and I think I showed you this one famous paper from Gang's group in 2011. So they show that indeed, just by simply reducing the environmental dielectric constant by suspending the graphene material in vacuum, you minimize the denominator of this formula easily, and there is no way to even to decrease more because it's the minimum you can get experimentally. And the electron-induced interaction will make the direct cone V-shaped and enhance the Fermi velocity. That's already a known phenomenon, but this experiment was published a long time ago. There were not really other works try to follow to continue to enhance the interaction and see what's going on there. And that's what we saw in the previous section, that in monolayer case, we can use this kind of regular crystal to fold the band and to enhance the electron interaction to have even sharper cones and to see a more robust quantum Hall. And now let's look at what's going on for the two-layer case, because whenever we say if you have a surface band which forms a regular crystal, the charge transfer between monolayer and interactions is defined, or let's say related to the band structure. When the system changes from the direct dispersion to a massive dispersion of bilayer, and especially when you have kind of these kind of subtle band gap openings, the whole thing from a DFT calculation point of view will change drastically, and experimentally also. So let's review quickly the theory again. If you remember that when we have a crystal which is insulating itself, this, for example, chromium oxychloride, and I don't know how to pronounce that, triiodine, okay? For example, these two materials, when they are placed subjected to a vertical electrical field, the surface space will become a regular crystal. All these things have a wavelength of about 5 to 10 nanometers. And these 5 to 10 nanometers, you can kill it. You can just remove them from 0 to 5 to 10 nanometers. So there is a phase transition within one single device, possibly happening. And if you place a system on top, in this picture is monolayer graphene, the direct dispersion. So the gap of direct cone opens slightly, and there is a sharpening of the cone at the vicinity of CFP. And this is for the monolayer case. And the picture is just like that. So you have a monolayer superpotential, monolayer-like, let's say, not direct monolayer. And the material systems are, we already knew that, are given in this table. And there are two of them already experimentally checked to be correct. So for bilayer case, we do some fabrication from lithography and the stacking of dry transfer heterostructure. We'll have a very clean interface of bilayer graphene and chromium oxychloride. And the whole structure looks like this. We will pronounce that BLG. And you have two layers of encapsulating, with the top one being HBN and with the bottom one being chromium oxychloride. The whole device is fabricated into the whole bar so that we can measure IXX and IXY with the two gates applied from top and bottom. So this is how it looks like. And this one I already showed you in a very long time ago, in 2010, when I started my PhD. People tried hard to investigate this single hyper gap opening in bilayer graphene. When you have a large enough displacement field at the charge neutrality, which is an n equal to 0, this line, you will have a resistive peak showing up to 10 to the power 9 or 10 to the power 8, which is already very good in terms of off-state current, because for 1 giga ohm, you will have only 1 nanoampere current if you apply 1 volt, okay? But if you replace the whole system, nothing big deal, but just changing the bottom layer of HBN into another new compound that can provide you a Wigner crystal or a kind of CDW, you will have a new form of resistive peak from this picture A into picture B. So this one we can see that there are very, very different features of the red regime. If you look at this color scale, I'm sorry, seems to be the projection is not very clear, but you can see the red parts are 10 to the power 10 ohms, which is 10 gigohms. So the maximum can obtain ever in graphene. Suppose if graphene is not able to open any kind of gap as large as this one, so there must be something happening here. So we can just understand the physics behind using the same things.
So between the, for example, the gap in this twisted structure, the Waals gap that opens, is smaller than you don't get such large resistance from that, for example.
The more they open the gap.
Yeah.
First of all, Are you talking about magic angle gap?
Yes, for example.
So magic angle is not strictly a gap, so it's a flat band.
Okay, but then due to more interactions, I guess.
So it looks like this exactly.
Yeah.
And this bandwidth
Yeah.
within the band, let's say Fermi level is here. This bandwidth is about experimentally 50 milliev. Theoretically 10. Same order of magnitude.
Okay.
And there's a further gap opening if you tune above the Fermi level. This has to be gapped, otherwise the whole dispersive gap band will be merged together with that. This gap is also very small. It's at the order of like 3 tenths of milliev. Very small gap and here too. That's why if you push further, you can even, without breaking down the ladder, you can even go to that region. And this gap, let's say, is also, if you compare with the room temperature 300K, which is 25 milliev, which seems to be large enough, right? But it's far away from the Fermi level of charge neutrality from the zero. Okay. And all you probe possibly within is 10 to the power 13 centimeter minus 2, you are most likely staying within this region. So you will go to the band edges of this, they call that band insulator, in these two ends. But within that, unless you're partially filled, you are conductive, right? That's how you get, and especially if you measure that at room temperature, you'll get a U-shape field effect curve. So the let's say conductivity has a minimum like this. Only when you cool down the system, you will have a partial field gap showing up at the end of the end. Grow. So at room temperature, you will have only a U-shaped field transistor, which is not insulated. That's very good. Okay. So it's just not insulated yet.
Yeah.
You have to cool down there at low temperature.
Yeah.
And that gap doesn't give you debond resistance.
Yeah.
So, yes, Alicia, please.
What is the distinction between this distinction between big increase and charge density? You use it interchangeably, but how do you define, like for this simple terms, how do you define this?
Yeah, that's a very good question. So even now, myself is also, confused between CDW and crystal. I would say in the family of CDW, it's like a pair's instability. You have electrons bound to the lattice of your material, so it's always commensurate with your material itself. So if you go there, you probe at each atom site, you will have a localized electron wave function. But within a crystal, it's not strictly bound to your material. It can be larger, a lot larger in the wavelength, and more freer in that sense. So, for example, within a crystal can happen in quantum wells. CDW cannot. Yeah. Okay. So I think today I'm going to have a break in the middle because I almost fell asleep myself yesterday. Let's have a 5 minutes break, okay, and come back later. Thanks a lot.